Okay, so now we have the last speaker of the first session of second part of day 5, who is another great mathematician, Francis Bonahon, from University of Southern California and Michigan State University. And he's going to talk on transparent SLD skeins.
Thank you. So in his talk on Monday, my academic brother proved the theorem that the two of us had known Lou for over 45 years. Actually, I think it's the estimate is not sharp. I think we had met Lou a few months before that conference in Wales. Okay. And so in those days, Lou was preaching the gospel that Skein relations were a good way to understand the Conway polynomial of a knot, which is the same, which is a variation of the Alexander polynomial. And then I lost my, and then shortly thereafter, like 3 or 4 years later, came the work of Jones to introduce the Jones polynomial. Sorry, I clicked the wrong, okay, which is another type of invariant. And if you look at Jones' paper, there is the Skein relation there. And I think it's really due to Lou's influence, because I don't think Jones would have known about Skein relations without Lou. And so, and that polynomial was very weird for us because it was completely different from anything we had considered before. And then it was better understood using the Kaufman bracket, which is an invariant of knotted links. Now, what these knot invariants have in common is that these are combinatorial recipes that are invariant under Reidemeister moves. And so shortly thereafter, once these things had settled a little bit, Reshetikhin and Turayev explained to us how we can, that combinatorial recipe that is invariant under Reidemeister moves can be explained in terms of representations of a quantum group. And they extended these to links where every component is weighed. I mean, the physicists say colored by representations of a quantum group. So here it's a picture of a link where the blue link is colored by the representation V1, and the other component is colored by the red color V2. And so examples, well, if you take the quantum group UQ of SL2, by the way, in this talk, I'm going to use the word quantum group a lot, but you do not need to know what it is. You just need to know that it's an algebraic machinery. It's an algebraic object that has representations. And so if you take the simplest quantum group, which is UQ of SL2, and you take the simplest representations of UQ of SL2, what you get is the Jones polynomial, or more precisely, the Kaufman bracket of the knot. If the UQ of SL2 has more representations, and in this way you get the so-called colored Jones polynomial, or going from 2 by 2 matrices to D by D matrices, namely going from SL2 to SLD. So you have a quantum group UQ of SLD. And then if you apply the Reshetikhin-Turayev machinery, what you get is the Helmholtz polynomial, where you specialize one variable to t equal q to the power d. Right? So to some extent, that encapsulates the Jones polynomial and the Helmholtz polynomial. Okay. And the idea, the reason why quantum groups are useful is that the general idea to construct these invariants is when you have a crossing between two components, one with the color V1 and one with the color V2, then you associate so V1 and V2 are vector spaces, and to the crossing, you associate a map from uh, a map from the tensor product of V1, V2 to V2, V1. See, V1, V2 is here. V2, the tensor product V1 is there. And that map is the so-called R matrix coming from the representation theory of UQ of the quantum group. And to some extent, the third Reinmeister move is equivalent to the Yang-Baxter equation, which is written below. And what turns out is that representation of quantum groups are useful way of constructing solutions to this Yang-Baxter equation. So that's why they are so useful. Okay, but then prior to reshooting into IF, actually, Witten had explained the Jones polynomial in a different way, in a more gauge theoretic way that worked in any three manifold. And so you can extend that construction to links in three manifolds where each component is weighed by a representation of a quantum group. So it's a complicated machinery. But what it does is that given a link in a manifold, in the three manifold, then it associates a polynomial, namely a number. Okay, so I like to compare that to the development of homology and cohomology. If you go back to the 19th century, in the 19th century, people knew about cohomology very well, because to a surface, you do Stokes and you associate a number. But it's towards the end, at the junction between the 19th and 20th century, that Poincaré had the idea that you understand better things by considering homology, which is a dual object. So the Skeins module is like the homology, whereas the previous constructions were cohomology, if you want. And so what you do is that if you think about, if you reinterpret what Witten does, the Skeins module of the three manifold M, the G Skeins module, associated to a Lie group with the Lie algebra script G, is you take all possible framed-oriented links in the three manifold colored by representations of this quantum group, and you take the free module generated by that, and then you kill all relations between tensor products of representation of UQ of the quantum group. Okay, it's horrible, and it's, of course, if I say it like this, it's unworkable. However, at least in the case of SLD, so SLD, by the way, it's D by D matrices with determinant 1, in case you forgot. And where Q is generic, Cotis, Kamnitzer, and Morrison, they figured out what all these relations are, and they came up with an explicit presentation for the Skeins module in terms of, so it's instead of using links, it's actually smarter to use something called webs, which are trivalent graphs. And then you have Skeins relations, which are much more complicated than the relations of the Kaufman bracket. Namely, it's a much longer list. However, the spirit is exactly the same. Namely, it's a combinatorial object defined by pictures. And it's important for us, it's the mathematics of the Helmholtz polynomial. Okay. Now, again, quantum groups in particular, I mean, you know, I personally started as a geometric topologist. Quantum groups have always been an acquired taste. It's very complicated, just looking at the definition. It's very intimidating. However, there is something much nicer to consider, which is so it's not, instead of using UQ of the Lie algebra G, you consider something called OQ of the Lie group G. And what this OQ is, the quantum coordinate ring there. So it's also a bad definition, but it's the Hopf dual of the previous one. So these two have a structure of Hopf algebras, and so there is a duality between the two. And that one, however, for a geometer, it's much more intuitive. Actually, at the end of my talk, I will just express everything in terms of multiplying matrices. Uh, so geometers, we have quite a bit of intuition about Lie groups. That's what geometry is about. Whereas Lie algebras, the algebraists much prefer that. It's algebraically much simpler. But for us, it's a little hard to get the intuition there. Okay, so that's a little bit of an advertisement as a side comment. Okay, so in general, when you construct quantum invariants, or if you consider elements of the Skeins module, there is a big difference between overcrossing and undercrossing. Well, okay, we know that. However, the focus of my talk is that weird things happen when the quantum parameter Q is a root of unity. And then in that case, you have certain red colors so that you can cross the red color without changing anything. In other words, the red color will be transparent. I realized that the title I gave for the conference was invisible. Yeah, I have a problem. I'm using the two words the same way. Okay, the talk says transparent. You can also think of it as being invisible because you can cross it without noticing anything. So here is the theorem. So first of all, by the way, as you read on my first slide, this is a joint work with Vijay Higgins, who's now at UCLA. And so first thing is that these Skeins algebra, I wrote it depends on Q, but actually it depends on the choice of a D root for Q to the power 1 over D. And suppose that this D root is an nth power of unity. And then there is an additional condition that I wrote very small because it's a technical thing that we need for our proof, but it's probably not necessary. So forget about it. It's finite Leibniz conditions for Q, depending on the dimension. And we can forget about those. Then there exists D-1 magic representations of UQ of SL2 that gives transparent elements in the Skeins module, in the sense that if I have a link L that is colored with these transparent colors, which are red, and if I take any other blue link, any link with the blue color, the blue color can cross the red without changing the element in the Skeins module. So in other words, that these colors are undetectable. Well, so this was found, so this is for SLD, namely for the quantum group based on D by D matrices. In the case where D is equal to, the first example was found by Helen Wang and myself, and it's based on Chebyshev polynomial of the first type. You don't need to know what that is. And that has generated quite a bit of work. Because first, we had used it a little bit to understand representations of the SL2 Skeins algebra. The SL2 Skeins, that's another word for Kaufman bracket. So for the Kaufman bracket Skeins algebra of a surface, so we started that with Helen, and then to some extent our program was completed by these two groups of Charlie Froman, Joanna Kania-Batrushinska, Tangley, and then a more algebraic team of David Jordan, Jordan Ganev, and Pavel Safronov. But also to get some structure theorems for the Kaufman bracket Skeins module of three-dimensional manifolds. And so it's essentially the same people, but also had Renaud Decheri, Adam Shikora, Efi Kalfagiani. So actually, if you went to the talks by Adam Shikora, Efi Kalfagiani, or this morning, Joanna Kania-Batorczynska, you probably heard about these things. And so the question was, these Chebyshev polynomials of the first type, which were completely unexpected for quantum topologists. So why should these be involved? Should these appear? So with Helen, when we did that, we had no clue what we're doing. We're following our nose using by hand methods. And in particular, I like to say that it was really important that we didn't know that there existed Chebyshev polynomials of the first type and Chebyshev polynomials of the second type, because the ones of the second type were a little more familiar to quantum topologists. The one of the first type was more familiar to a hyperbolic geometer like myself. And if you believe that they are the same, well, things look more promising. So actually, these raised our hopes. And then after that, well, we had to change. Eventually, the proof converged. But we had no clue what we were doing. And to some extent, going to D, replacing D equal to by general D is a way to really understand what's going on. And what's going on, it has something to do with the fact that when you take nth powers, very often things simplify. And that's a variation of the famous property of Frobenius, which is that when you work in prime characteristic in a ring with prime characteristic n, you have that x plus y to the power n is equal to xn plus yn. So you have these miraculous cancellations for nth power when n is the characteristic you're working in. So it's something, without the condition of the characteristic is well known to our calculus students. And with the prime characteristic is something you see in an introduction to number theory, undergraduate number theory. And but what's not so well known, it's also true in quantum algebra, where the two variables, they don't commute anymore, they q-commute with the scalar, namely so that yx is xy with a scalar in front, and where the scalar has the property that q to the n is equal to 1, because what happens is that you have a quantum binomial formula, and the quantum binomials all disappear in the big formula, except the first one and the second one. I mean, the proof is the same as the one you see in characteristic n. Okay, and so we want to do the same thing, but taking nth powers instead of these objects. We want to take nth power of matrices. 2 by 2 matrices for UQ of SL2 and D by D matrices for SLD. Okay, and so let's try to understand nth powers of D by D matrices, or so either in SLD of C or in the quantized version, which OQ of SLD. Again, you don't need to know what that is. It's just more complicated than the D by D matrices you encounter in sophomore linear algebra class. But you want to do it up to conjugation. I mean, you know, we are topologists. We want things to be independent of base points. Okay? So things invariant up to conjugation. So let's try to think about it. If I have a matrix, well, most matrices are diagonalizable. And so up to conjugation, a diagonal result matrix, it's the same as the list of the eigenvalues. So the conjugacy class of a generic in this case means diagonalizable matrix, is determined by the unordered list of its eigenvalues. Okay, so there is no, or you cannot decide which one is the first eigenvalue or the second one or the 17th one. So there is no specific order. And what you know is that if you're going to study numbers, a list of numbers that are not ordered, the good way is to consider symmetric polynomials in these numbers. And then in these symmetric polynomials, there are fundamental ones that are the elementary symmetric polynomials. I mean, you have one for every k, and what you do is that you take all monomials of length k where with the distinct variables. So now, so you can have one from k to 1 to actually d, but for k equal d, you take the product of all the eigenvalues. This is called the determinant, and the determinant in SLD, it's equal to 1, so it's not very interesting. So we're going to stop at d minus 1. Okay. Now, there is another name for these elementary symmetric polynomials in the eigenvalues of a matrix. That's called the coefficient of the characteristic polynomial, up to sign. Because if you, when you compute the characteristic polynomial, if you compute it in a base where the matrix is diagonal, then you're going to get these elementary symmetric polynomials as coefficients, up to sign. And then if you are more representation theoretically oriented, you can see these as a trace, because what you do is that if you have a matrix, it acts on the space of dimension D. Okay, and therefore it acts on the kth exterior power of that space of dimension D. And if you look at the trace of that action, that's exactly these elementary symmetric polynomial in the eigenvalues. Okay, so you see these are important because they characterize the conjugacy class, and they have you can interpret them in terms of representation as trace functions. Okay, and now if I have a matrix and I want to take the nth power and I want this kth trace, what can I say about it? Well, namely, if you think about it, they characterize the conjugation class of A. So how can I characterize the conjugation class of A to the power n? And so there is a very old theorem which says that the k-trace of A to power n, I can express it as a polynomial in the k-traces of A. And the reason for that is the very old theorem, going back to Euler and Newton and people like that, that says that if I consider all symmetric polynomials in the values, you can express it as a polynomial algebra in the elementary symmetric polynomials. So this is just from the theory of symmetric polynomials. And in addition, it's explicit. So you can explicitly compute them. So for instance, here is one, P572. So 5 means that I have 5 variables. I'm taking the 7th power and I take the second trace. And it's a polynomial like this, where in the traces from S1, S2, S3, S4. Since D is equal to 5, I have 4 traces. So the second trace is given by this polynomial. So it's completely explicit if you can use a computer. Now, when you have a polynomial with integer coefficients like this one, you can do lots of things in it. So for instance, you can plug in numbers into it that's going to give you a number. But what's not so well known is that you can also plug in a representation of a group or anything actually. Because let's try to, and if you plug in representations, you're going to get another representation of the same object, which has the property that for every element of the group, the trace of the image of the group and this representation is going to be obtained from the traces under the the representations I was given, plugged in to my polynomial p. So that's a way, given a polynomial with integer coefficients, you can create a new representation. So why is that? Well, if you have a polynomial with integer coefficients, you can express it with two operations. You take products and you take sums. And if you take a product, if given two representation, if you want the, say, row 1 and row 2, if you want a representation such that the trace under that new representation is equal to the product of the traces of row 1 and the trace of row 2, well, the tensor product will do that. So that's a simple example. Much simpler is if you want the sum, you take the direct sum, and in this way, the trace of the direct sum is the sum of the two and of the trace functions of the two representations you started with. Now, and so in this way, by taking a succession of products and sum and product and sum, you're going to get all possible polynomials with integer coefficients, except you only get the ones with non-negative integer coefficients. And I didn't say, if you look at the example before, there are negative numbers here. So I certainly want also negative numbers. So given two representations, do you know a representation whose trace function is the difference between the trace function of the first one and the trace function of the second one? Well, for the sum, that was the direct sum. And for the difference, it's the direct difference, except that this direct difference does not really exist as a representation. It only exists in a k-theoretic sense. Namely, so the object is known as the representation rig of the group G. And so it's a representation with quotes. And actually, if you go back to something I said, to my previous slides, and if you look at the way where the place where I stated our main theorem with Vijay, you might have noticed that I said that there were representations with quotes, Z, N1, Z, N2, and so on. So these are not real representations. They only exist in a k-theoretic sense. However, so that looks very abstract, but in practice, you're just taking linear combination of trace functions. So that's the threading operation that was appearing in, for instance, Joanna's talk this morning. So much simpler. Okay, so in this way, we can plug in representations into any polynomial with integer coefficients. Okay, now remember that I'm interested in these polynomial here, which has the property that it expresses the k-trace of the nth power of A in terms of the k-traces of A. Okay? Now, I also told you that each of these k-trace is actually the trace of the exterior power representation. And so if I apply the previous principles, that gives me a representation which has the Z and K, except it's a representation with quotes. And that gives me a representation obtained by evaluating the polynomial P and K into these exterior power representations. And it has the property that the trace of A for the representation is the K trace of A to the power N. Okay, now this looks very fancy. This is actually classically known as the Adams operation, named after John Frank Adams. Apparently, I haven't been able to track this down. Apparently, it's in his famous papers on finding linearly independent vector fields on the sphere. That's okay. And so once you have a construction like this, there is what I would call standard quantum group technology, where you can put Qs everywhere. You can quantize this picture. And so the representation by exterior powers determines a representation of the quantum group associated to SL2, and it goes to a quantum exterior power, blah, blah, blah. So you just put Qs everywhere, and then you can plug them inside of these polynomials to determine a representation with quote of the quantum group UQ of SLD. If you remember by advertisement, it's actually better to think of this as co-representations of the quantum coordinate ring. So on the other hand, co-representations, that's a little more of an acquired taste for us geometers, but okay. And then, so the theorem with Vijay is that there are these representations with codes, Z and K, which are transparent in the sense that when you use them to color links, you can cross the link without changing the element in the Skeins module. So, and the proof, you just manipulate, it's a proof by picture obtained by manipulating webs, these trivalent graphs in the three manifold. Okay, so if you think about it, the proof that looks exactly like the kind of thing Lou would like, right? It's pictures, and indeed it's like a Lou type of mathematics, the proof. However, the statement, K-theory, even representations of quantum groups, that's not his style. And the truth is that he and I have something in common. We like our mathematics to be concrete. So in the remaining 10 minutes or so, I'm going to talk about something different, which is clearly related, except we don't know why, how. On the other hand, it's very concrete, and you can see it not on pictures, so Lou would be unhappy with that, but at least on computations. And so I'm going to show you that thing. And it has to do with miraculous cancellations for quantum matrices. Okay, so let's consider quantum matrices with coefficients or with entries in a certain algebra. So what's that? Well, so formally, if you want to be it's an A point. So if you want to be abstract, it's an A point of the quantum coordinate algebra of the quantum the space of D by D matrices. Okay, and what an A point, that's an algebra homomorphism from this algebra to my algebra A. Okay, that's horrible if I say it like this. But in practice, it's very simple. It's a quantum matrix is a matrix which has entries. It's a D by D matrix. And and where the entries are in my algebra A. But instead of commuting, they satisfy certain relations. So these ones are ugly. Eh? And there is a motivation behind these relations, which I don't really have time to explain. I just want to show you what they look like. Most of the relations just say that the entries Q commute according to certain rules having to do with the indices, which index here is greater than that index there. And then you have the bad one here, which looks like a 2 by saying that a certain 2 by 2 determinant with a Q is equal to another 2 by 2 determinant with a Q. That's another rule. So it has to do with a certain deformation of actually the space of dimension D, something which is the quantum D space. But just think that there are certain relations which are natural if you like these kind of things. And a problem is that quantum matrices do not multiply well. So in particular, if you take the nth power, it is a quantum matrix, but not with coefficients in A, my algebra. It's in a tensor product of A. That's ugly. However, you can give an and you can give you can go around the difficulty by defining the nth power in a funny way. So we have this K trace for usual commutative matrices, and there is a quantum version of those for a quantum matrix. And to some extent, they generate the conjugation invariance of quantum matrices. So there is a notion of conjugation invariant. It involves co-adjoint representations, and so you can make sense of that. And however, look, it's fairly in practice. It's simple. Let's do it with 3 by 3 matrices. So D is equal to 3, and you have one of these traces from 1 to 3. The first one is the regular trace. The second one and the third one, I wrote them there, but look, if you look at the last one, it looks like the determinant of this matrix. It's just that it got Q's. And also, remember, it's really important because these guys do not commute. It's really important to make sure that you take them in the correct order. But so the cues are there actually to guarantee that you do that. But it's a relatively natural notion. This is just the determinant. Here, it's the second coefficient of the characteristic polynomial. Well, if you write the characteristic polynomial, it's going to look like this exactly when Q is equal to 1. I mean, in the non-commutative context, where Q is equal to 1, you get the second coefficient of the characteristic polynomial. These are relatively nice formulas, right? Okay. And you remember that for a commutative matrix, for a non-quantum matrix, the way I get the k trace of a to the power n is by plugging the k traces of a into this polynomial. So I can do the same. I want to do the same for quantum matrices. And what's lucky is that my quantum k traces that I gave you before, they commute with each other. So you have no ambiguity in terms of plugging them into your polynomial. And you can define the conjugacy class of a to the power n by the family of these quantum k traces obtained like that. Okay, so you can always define that, but let's do it in practice. So D equals 3, so 3 by 3 matrices. I'm going to take the 5th power. Okay, so here are my quantum K traces, and the polynomial to get the quantum trace of a to the power 5. It doesn't exist really, but okay, I'm going to pretend it exists. And it's obtained by plugging these guys into this polynomial. I said the polynomial was explicit. There it is. And so you plug in those guys into this formula, and you can do it. Well, okay, it's a little long, so it's on the next slide. Okay, except that you see there is a dot, dot, dot here because it's the end is on the second slide, and but it's there. You can compute it. Come on, if you think about it, it's supposed to be the trace of a to the power 5 when q is equal to 1. You know, it's a complicated formula, right? But it's that. So you can do it, but it's ugly, right? Unless you have a q is the root of unity. Because when q is the root of unity, my formula in the previous two slides boils down just to this. Namely, everything disappears, and I'm left with only three terms. And if you look at the three terms, this is the usual trace of this matrix here, where I take uh, which I obtained from the original matrix by raising each entry to the power n. Okay, let's check another example. I take the second trace. So same situation. That's the polynomial. It looks like the previous one, but it's slightly different. And there is a 2 here. The previous one, there was 1. And then you compute, and you find this. And again, it's like this formula here, except you replace q by 1, and you raised it's this formula here, sorry. You replace q by 1, and you raised all the entries to the power 5. Namely, it's the second trace of that matrix of power 5s. Okay, and so it turns out to be a... So with VJ, we started with this. Actually, there is a SAGE program which enables you to do computations with quantum matrices. And we started with that. We ran the computer to see if a property like this would be true. And once it was clearly true in SAGE, we made it a theorem. And the theorem is the following. So you start with a quantum matrix. You take not the power of that quantum matrix, but the matrix of the powers. Namely, you take the same matrix, but you raise all the powers, all the entries to the power n. And if you go back to the relations of quantum matrices, you can see that this one, everything commutes. Namely, it's a non-quantum matrix. Right? So it's a usual matrix. The entries commute with each other. So it's as good as having numbers. And then the theorem with VJ is that if Q is a primitive n root of unity, and if n is odd, it doesn't quite work with n is even. So I don't know exactly what's the correct statement for n even. Then the k trace of a to the power n, which we had defined by plugging the k traces of a into our favorite polynomial. That's just the k-trace of that stupid matrix obtained by raising everything to the power 5, to the power n, which is what we saw on the previous two slides for n equal 5 and d equal 3. So it's really a Frobenius type of results. And so this is the kind of concrete mathematics that I really like. And I think the approach of Lou to knot theory is also exactly in the same vein, drawing lots and lots of pictures and then proving theorems based on that. So happy birthday, Lou. Thank you. By the way, so that's the reference for the first half of my talk. The paper has appeared The second one, we will write it up at some point, but I don't know. Yeah. Thank you. Any questions? Yeah, that's the problem with this online congress. That giving talks over Zoom gives me PTSD from the days of teaching during the pandemic. Uh, I used to have, so when I was teaching during the pandemic, I would always require a couple of students to turn on their camera. And one of them was also the haha student. Namely, that student was supposed to say, mm-hmm, mm, uh-huh, uh-huh, haha.
Oh, it's easier to percolate
Oh,
questions slowly when we go out to the restaurant or take a walk and so on.
Yes,
Although,
and also the beer is not as good. Yeah.
excellent. Thank you for a fantastic talk. Let me let me stop recording.